This is problem 73 from chapter 14. The roller coaster car has a mass of 700 kilograms, including its passenger. If it is released from rest at the top of hill A, determine the minimum height h of the hill crest so that the car travels around both inside the loops. Inside both the loops? Without leaving the track? Neglect friction, the mass of the wheels, and the size of the car. What is the normal reaction on the car when the car is at B and when it is at C? The radius of curvature for B is 7.5 and the radius of curvature for C is 5. And because the height of B is 15 and the height of C is 10, that means the radius of curvature would be the radius if it was a circle. Although it doesn't look much like a circle in my drawing. And it doesn't have to be a full circle, but it could be modeled as a circle at the top here. There's something useful that you could either remember, or if you don't remember it, you could derive it, and that is what the minimum velocity would be to travel upside down on the inside of this loop. So let's pretend we don't remember it and derive it for practice. So you would have a normal force acting downwards, but at the minimum velocity at which you could safely travel around this loop, the normal force is equal to 0. If you go any slower than this minimum velocity, you fall to your death. Well, maybe. You fall in any case. So you have the force of gravity acting downwards, and remember from when we did normal and tangential components, you have to have an acceleration pointing in the normal direction, and that acceleration is equal to v squared over rho. So we have one force acting downwards, and that must be equal to the mass times v squared over rho. This is Newton's second law in the normal direction. Mass cancels out. Solve for the velocity. This is the minimum velocity because I said the normal force was 0. So there we have it if we didn't remember it. The minimum velocity at which you can safely go around inside the loop is the square root of g times rho. Now, for B, that minimum velocity is 9.81 times 7.5, which is 8.578 meters per second. And at C, the minimum velocity is going to be smaller because the radius of curvature is smaller. Now, looking at our equation here, well, first I guess we should do a free body diagram for the cart. We have a force of gravity acting downward. We have a normal force acting perpendicular to the surface, but because it acts perpendicular to the surface, the normal force is also perpendicular to the displacement. Therefore, the normal force does no work. And because we are neglecting friction, that is the only force that we have other than gravity. Therefore, we have no other work done. At point A, we're starting with a velocity of 0, so this becomes 0. So your height at any point along the track, determines your velocity at that point. If you're starting from this height, what is this? That's what we're looking for. So if you're starting from this height at rest, you can find the velocity at any other point just by knowing what the height is. So then you have, if this height is known and this height is known, and well, yeah. I mean, I was going to say and the mass is known, but it doesn't really matter, does it? Because the mass here cancels out. So if you know your initial height and your final height, you can determine the velocity. So we have, let's pretend we know the height. So we have a known quantity on this side. The greater this height is, the smaller the velocity would be. So you're going to be going faster at point C than you are at point B, but the minimum velocity that you need at point C is smaller than the minimum velocity that you need at point B. So if you're safe at point B, then you are also safe at point C because the height is smaller and the radius of curvature is smaller. Okay, so we really only need to be worried about getting around the first loop safely. So I'm going to say my final velocity here is what I have at point B. The height is what I have at point B, and that will allow me to find the minimum height that I need to make it around loop B safely. So this is 9.81 times height A is equal to 1/2 times the minimum velocity that I need to get around loop B safely, which is 8.578 squared, plus G, which is 9.81, times the height of loop B, which is 15. And that gives me 18.75 for the minimum height. That was one thing I had to find. Well, I have to find the normal force at point B, but we said if we're using the minimum velocity, the normal force is equal to 0. So the normal force at point B is equal to 0. So finally, we just have to find the normal force at point C. So we're going to use this equation again, but now at point C. It is still true. If I say my initial point is point A, it's still true that the initial kinetic energy is 0. I could, if I wanted to, make the initial point B and the final point C. It doesn't really matter. You would still get the same value on the left-hand side of the equation. So I'm going to say this is G, which is 9.81, times H1 would be 18.75. You can see from this equation here that if you used B for the initial point, since this is equal to this, you'd still get the same thing. Let's figure out what this is. 9.81 times 18.75 is 183.9. And then just bear in mind that I did cancel out the mass, so that's not actually the initial gravitational potential energy, it is just G times H. The fact that the mass cancels out is rather nice, so that if your friend safely goes around loops B and C on the roller coaster, then you can be pretty confident that you will make it around loop B and C safely as well. Okay, so now we're doing this at point C. So this is 1/2 times the velocity at C squared plus G times the height of loop C, which is, whoops, I guess I want to call that 9.81, times the height of loop C, which is 10. So I have the speed is equal to 183.9 minus 98.1 divided by 1/2. I could have said multiplied by 2. And then take the square root, and we get 13.1. But we were asked to find the normal force at C. Well, so we can do something similar to what we did here, but now the normal force is not going to be equal to 0. So we have the roller coaster cart upside down at point C, and we have a force of gravity acting downward. We also have a normal force acting downward. Using Newton's second law, in the normal direction, the normal force plus the force of gravity is equal to the mass times the normal component of acceleration, which is v squared over rho. Therefore, we can say the normal force at C is equal to mv squared over rho minus m times g. The mass is 700 and it appears in both terms, so let's pull that out front. V is 13.1, so this is 13.1 squared divided by rho, which is 5 when we're at C, minus, I already pulled the mass out, so this is minus 9.81. And that gives us 17.2 kilonewtons. We found the normal force at B, the normal force at C, and the minimum height needed to ensure a safe ride.